minimum entropy, and maximum order, whereas liquids have maximum entropy and minimum order. The greater the disorder or randomness in a system, the larger the entropy. The entropy of a substance always increases as it changes state from solid to liquid to gas. When a pure solid or liquid dissolves in a solvent, the entropy of the substance increases. When a gas molecule escapes from a solvent, there is an increase in entropy. Entropy generally increases with increasing molecular complexity. Reactions that increase the number of moles of particles often increase the entropy of the system. Here's a question for you, buddy. Which of the following reactions results in the largest increase in entropy? A. CO2-CO2, B. H2 plus Cl2 to HCl, C. KNO3-KNO3.
All of the reactions result in an increase in disorder, but A, in which CO2 moves from a solid state to a gaseous one, represents the largest change in disorder. We can calculate entropy using a table of standard values in much the same way that we calculated enthalpy earlier.
So that was the nice interaction between learner and tutor about the enthalpy
perspective. Then.
Now let me see
What's the picture?
another
In this molecular dynamics
video.
calculation, each pair of atoms is programmed to interact with a realistic interatomic force.
So then what really happens when a warm body is brought into contact with a cold one? Thermal energy spreads from warm to cold until both bodies reach the same temperature. This is the state of thermal equilibrium. At first glance, thermal equilibrium seems everywhere. Nature seems impelled toward the state of equilibrium. Hot bodies and cold ones striving toward the same temperature, and falling bodies turning perfectly good work into useless heat. From the physicist's point of view, when nature tends to behave in such a universal fashion, there must be a scientific explanation, and there is. The explanation began as an idea, of course, an idea for the construction of a better steam engine.
There was a young man named Carnot, whose logic was able to show, for a work source proficient, there's none so efficient
As nature would permit, and the logic to come pretty close.
given a difference in temperature, a high temperature, T sub I, and a low temperature, T sub O. Carnot designed.
In Carnot's ideal engine, the ratio of the heat taken in to the heat wasted was the same as the ratio of the two absolute temperatures needed to drive the engine. In other words, and this was the ideal that stemmed from Carnot's imagination, something that goes in is the same when it comes out. If it's not the heat, and if it's not the temperature, what is it? It's the heat divided by the temperature at which it flows. And according to Clausius, that's entropy. In a Carnot engine, some entropy flows in at high temperature, does its job, and the same amount of entropy flows out at low temperature. So an ideal engine not only conserves energy, the ice doesn't warm up while there's any solid left. Why?
A flow of heat causes the transformation of ice into water at a constant temperature. Therefore, in changing from ice, the water's entropy is increased.
And so, water is a state of higher entropy than ice. In fact, any solid is a state of lower entropy than the same matter in liquid form. Liquid is a more disordered, chaotic state of matter than solid is, and it has a higher entropy. On land, divided by the temperature. Remember, nature always wants to increase entropy. In this case, the entropy of the ice, plus the rest of the universe. If the temperature is very small, it's very bad indeed. Melting the ice would cause a big decrease in entropy of the entire universe. If the temperature is big, it's not so bad. The combined entropy increases when ice melts. That's why, in the grand scheme,
if you had a movie of that, you'd be able to tell instantly whether it was running forwards or backwards. Because when it's running forwards, the bounces of the ball get smaller each time it bounces. If you saw the bounces getting bigger and bigger, you would know immediately that the film was running backwards. Now what's happening in that case is that the energy of the ball is turning into heat, and that increases the entropy of the...
So that was regarding the entropy and enthalpy. Now work done on a closed system. Now first law of thermodynamics, where it is used and how it is useful. In fact, first law of thermodynamics states about the law of conservation of energy, which energy cannot be destroyed or generated.
An open system has got tremendous applications all across industries. Using this law, you can predict what's the pressure drop across a nozzle, or how much is the energy required by this pump to pump the fluid out, or what's the heat transfer in the heat exchanger, or what's the amount of work produced by this turbine. In a nutshell, first law simply means conservation of energy, or states that energy is getting transformed from one form to another form. We will understand how first law is applied for a thermodynamic system by analyzing a simple example, an example of piston cylinder arrangement. Here the cylinder has got some gas inside this, and assume there is no air leakage to the surrounding. So this is an example of closed system where mass doesn't change. Assume this gas is absorbing some heat Q from surrounding. Also assume that this gas is able to push this piston upwards due to high pressure of the gas. So this gas is doing some work on the piston with quantity W. There are two energy interactions for this gas. It is absorbing some heat and is also doing some work. So if we want to find out what is the change in energy of this gas, it will increase by a quantity Q because it is absorbing some energy, and it will decrease by a quantity W because it is losing some energy since it does some work. So you can write change in energy of the gas delta E as Q minus W. This is first law of thermodynamics for a closed system. And the same equation we can write in differential form like this as rate of change of quantities per unit time. Now what we are going to do, we are going to open this system or open the cylinder like this. Now the system is no more closed, it is an open system now. The mass is continuously varying. It can have an inlet mass flow rate of this much quantity with particular pressure and particular velocity. Similarly, there will be an exit flow rate of this much quantity and pressure and velocity. Here also our objective is the same. We want to find out energy change of the gas or the system. But which gas? The gas is continuously flowing. You cannot define a particular gas over here. So before proceeding to the energy change calculation, we have to define a system first, a control volume, where we will do energy balance. Here the dotted line represents the control volume or the space where at which we will do our energy balance. Here you can see there are 4 energy interactions to the system in total. 2 energy interactions which is coming to the system and another 2 energy interactions which is leaving the system. So if you want to find out energy change of the system, you can sum energy transfer due to this 2 interaction and you can subtract energy transfer due to this 2 interaction. So for an open system, rate of increase of energy of the system will be like this: heat absorbed minus work done plus energy transfer due to the incoming stream minus energy transfer due to the outgoing stream. The flow stream has got 3 components of energy: internal energy and kinetic energy. Finally is potential energy. Z represents the altitude of the flow stream. This equation is the first law of thermodynamics for the open system. But for an open system, the term W, the work done by the system, or in this case the gas, should be carefully examined. Here you can see gas is doing work to push the cylinder up, plus it is doing some work to eject the fluid out or to suck this fluid in. Or to maintain this flow, the gas has to do some work. And this kind of work which is required to maintain the flow, is known as flow work. So the total work done by the system will be summation of WCV and flow work. WCV represents the visible work, in this case work done by the gas on the piston. And we know flow work is the work required to eject the flow or suck this fluid in. And work required to eject this stream will be force at this area into velocity of the stream. And force is pressure into area. So you can represent flow work as this. And if you do some rearrangement to the equation by substituting the volumetric flow rate as mass flow into specific volume, and by representing U plus PV as a new property, the enthalpy, the above equation will be simplified like this. This is a final and most useful form of first law of thermodynamics for an open system. Now we will work out one interesting example using this equation. Here it is, a simple pump problem where fluid is getting pumped from point 1 to point 2. And we want to find out what's the energy required by this pump to perform this action. To find out that, we bring first law of thermodynamics for an open system into picture. And this is the equation. We can assume that everything is in steady state, so energy of the pump doesn't change with the time. So you can obviously put the first term as 0 because it is in steady state. And usually there won't be any heat transfer to the pump. So you can put that term also as 0. If cross-sectional areas of point 1 and point 2 are equal, then velocities at this point will be equal. So from this equation the velocity terms get cancelled out. You can also assume height difference between inlet and outlet are negligible. So the altitude term also get cancelled out. And finally what remains is this. Work done by the control volume or by the pump is mass flow rate into change in enthalpy. If you want to find out work required to the pump or to the control volume, then you have to just reverse the sign. Using the same approach, we can solve a lot of other energy transfer problems in industries. That is all about first law of thermodynamics for an open system. Thank you for watching the video.
So today we have discussed about the aspects related to temperature, specific heat capacity, zeroth law of thermodynamics and first law of thermodynamics. We will continue in the next time with some more theoretical aspects. Thanks to all of you.